Good morning. Nice to see everybody. And thanks for coming through the cold and through the storms. First of all, for those who are arriving from other places, welcome to Yale University and to the Forum on Climate Change and Infectious Disease Research. I'm Mark Pagani, and to the surprise of everyone that knows me, I'm the director of the Yale Climate and Energy Institute. And by the way, we're hosting this forum. And we're very excited about this. This is something we've been thinking about for some time, trying to integrate and bring together climate scientists and human health scientists, particularly in the field of infectious disease. This is something that we feel that is underappreciated, particularly in the United States. The climate scientists that I work with, I think, and many of those in the audience have a pretty good appreciation of the coming changes in temperature and in the water cycle and seasonality, and it just seems obvious that this is going to impact the underlying ecology of organisms that make you sick and the organisms that transmit that disease. And maybe I'm wrong, and maybe nothing will happen, but we simply don't know. And it's sort of shocking how underfunded this topic is through funding agencies like NIH and NSF. And without that funding, really, the exploration of the topic is severely compromised. And so one of the outcomes of this sort of meeting, and hopefully meetings in the future, will be to try to transform that funding scenario. So we're looking forward to the ideas that emerge from this forum, and hopefully collaborations. And that will proceed into tomorrow as well. I want to stress that this forum took a bit of time to pull together, and I want to thank the organizers of the event. And those include Maria Dirkwasser from the School of Public Health. Maybe you can just raise your hand so people can see who you are. And Trudy Storilmo from the Department of Geology and Geophysics, Derlin Fish from the School of Public Health, and our student intern, Rihanna DiBartolo Cordovano. And that's all I have to say, and I hope you enjoy the meeting and your stay in New Haven. Our first talk, let's get started, is Noah Diffenbaugh, is Assistant Professor from the Department of Environmental Earth System Science in Stanford University. Hey, Noah.
Hi, thank you, everyone, and thanks to the organizers for having me out and hosting this. Thanks to Mark for the support. This is an area I really want to echo Mark's statements about the importance of the area and kind of opportunities for new exploration. It's an area that I have a bit of funding from NIH, which is I put all the important parts of the presentation are right at the bottom. So there may be a pointer here. Okay, here we go. So most of that will be hidden throughout the talk. But we do have a little bit of funding from NIH, and actually just in the airport on the way here, emails are flying on some of that project that we're trying to get set up that I'll talk about a little bit at the end. But I think for me this is a really exciting workshop because I feel very genuinely that I have a lot to learn, and this seems like a great opportunity to do it. So the title here, the possible relevance, is really is very sincere. It's may not be relevant, we'll see, but I think it's an exciting area that's emerging in terms of this climate disease relationships. All right, so I want to just real quick acknowledge my members of my research group and in particular, Daniel Horton, who's working on some of this NIH work, who's a postdoc, and Martin Scherer, who's a research staff, has done a lot of, helped with a lot of the GCM analyses that you'll see. And these are collaborators on 2 NIH-funded projects. I'll show some, I'll talk a little bit at the end about the one project with Mark Kilpatrick and Laura Kramer, and Jordan is a graduate student with MARM, and Dan, as I mentioned. And then we also have a project with Karen Levy that's focused more on the hydrologic cycle and hydrologic extremes. But since this is the temperature talk, I'll focus on the temperature work at the end. So the work that's going on in my group is mostly focused around trying to understand the interface between physical climate processes and climate impacts. So we're trying to identify the phenomena, the physical climate phenomena that most directly and acutely impact natural and human systems, and then we're trying to work from that middle, that interface, out in both directions to try to understand the physical climate dynamics that shape those climate phenomena, and also understand the vulnerability of different natural and human systems to those physical climate dynamics, potential changes in those physical climate dynamics. So health and infectious diseases more specifically are an interesting and potentially very fruitful candidate for studying this interface. And you know, I'll actually show some work that's focused on corn, and not because I'm going to argue that people might get infectious diseases from corn, although maybe that's possible. I would be excited to shout now if that's possible. But more just to highlight kind of how we can go about using biological sensitivity to different climate conditions to understand potential climate change impacts when we have an understanding of those relationships, which I think we maybe have more so for corn than for some infectious diseases. All right, so I never know which room I'm walking into when I give a talk. So just a couple of real quick kind of, you know, atmosphere, ocean, climate dynamics 101 slides. These are from Marshall and Plum. But you know, the climate and weather conditions that we experience are a result of the energy balance of the planet, and really the imbalance of energy across the planet. And because of Earth's shape and the tilt of its axis of rotation, the amount of energy coming into the system is not uniform at different latitudes, nor throughout the year, and as a result, there is an excess of net radiation in the tropics, a deficit at the higher latitudes, and what we experience on a day-to-day basis in terms of the mean, which in Palo Alto it's kind of always like the mean, but in some other places it varies quite a bit, and both the mean and the extremes of climate are a result of this energy imbalance. And from time to time, there are really extreme events, and you can see over here on the black border of the screen, these are temperature anomalies from July 2003 in Europe, up to on the order of 10-degree temperature anomalies. This was certainly a 1 in 500 year event in terms of the temperature, the direct temperature record in Europe, or in parts of Europe, and it's been argued that it was a 1 in a million year event statistically, but certainly the summer temperature in much of Europe was on the order of 5 sigma removed from the mean. And so this was an extreme event statistically. And it was also a severe event in terms of the impact, and depending on who's doing the calculation and in what manner, on the order of 50,000 deaths associated with this heat wave. So this is one example where, oh, it's moving. Thank you. This is one example where these physical processes in the atmosphere, ocean, coupled climate system can have very very acute impacts, even on very short time scales. And I talked about the energy balance of the planet, and the reality is that we are altering the energy balance of the planet, and one of the primary ways is that we are altering the energy balance is through the emission of greenhouse gases to the atmosphere, including carbon dioxide, and this is the Keeling curve with which I imagine that most in the room are familiar. And so we want to understand what happens to the climate system as a result of this change in radiative forcing, the change in the energy input to the system. We want to understand how the physical processes in the climate system respond, and we want to understand what the possible impacts could be, as was stated in the introduction. And so what I like to do is take a look at that interface between the physical processes, such as what made the 2003 heat wave, those kinds of events at different levels of forcing, and try to understand, use the vulnerability of natural and human systems to try to identify processes of interest. We can skip over this. All right, so the first question I'd like to address real quick is, or we'll see how quickly, is how might global warming influence temperature extremes? And this is a figure from Diffenbaugh and Scherer that came out in 2011. And there have been other versions of this kind of analysis published elsewhere. And what this is showing is the percentage of seasons that exceed the late 20th century maximum. So if this is simply a counting exercise. If we look at the late 20th century and we count up, we find the hottest season, whether it's December, January, February, or June, July, August, and we find in each location the hottest year, hottest season that occurred, and then we look forward in a suite of global climate model experiments and just ask in each year, was DJF warmer or colder than that late 20th century maximum? If warmer, then +1, right? And we just count them up. And you can see that by the late 21st century, in this A1B scenario, and we can talk about the scenarios separately if people are interested, but that by the late 20th century, at around, in this case, around a little bit over 600 parts per million CO2, in the tropics, between 90 and 100% of the seasons are exceeding that late 20th century maximum, and in large areas of the globe, something like 3/4 of the seasons are exceeding that late 20th century maximum. And so, given the magnitude of these changes, we were interested to look at the time of emergence of this kind of unprecedented heat, right? If every season is above the late 20th century maximum, how quickly might that emerge in different parts of the globe? And so this is just an example of the analysis for one grid point near Palo Alto, inspired by Scherer et al.'s grid point near Zurich, for those who know the 2004 paper on the European heat wave. So this is just what we do at each grid point. We can look at the time series. We have all these realizations that have been donated to the international community by climate modeling groups from around the world in the CMIP archive. Each of those black lines is a different realization. And what we're going to ask here is, at what point is there never a season cooler than the late 20th century maximum? Right? And so the red line here is the first of all these realizations. The red line is has the earliest permanent exceedance. Right? So around 2022 or something like that. Here, this red line, this realization ceases to ever go below. For the summer, let's say this is JJA, ceases to ever go below the late 20th century maximum. And this is an ensemble. They're all getting the same rate of forcing, but there's noise in the system. There's differences in how the models are constructed. So there's a spread. There's an uncertainty in that permanent emergence. And this blue realization shows the last, that's the latest permanent emergence all the way out, and in fact does not emerge in the late 20th century. And the yellow is the median. So there's a distribution. We can calculate the distribution of the dates of that last occurrence below the late 20th century maximum, which we call the permanent exceedance, the date of permanent exceedance. And if we look at this in map view, this is the top row, ignore that. I took the top row out. So this is the decade of the last occurrence of the season that's cooler than the 1980-1999 maximum, and I'm showing the median here. So that yellow line. And in the supplementary of the paper, we show the earliest and the latest in the 25th and 75th percentile. But what you see first, at least what I see first, is all of this dark purple. Bill, I don't know if it looks purple or not, but Bill and I on the way over were talking about color scales and visual perception. It looks purple to me. So what this is saying is that there's a 50% likelihood in this ensemble that these purple areas within the next 2 decades will emerge entirely from the late 20th century temperature distribution in terms of the seasonal temperature. Right? So that never again, there's a 50% likelihood that these areas will never again experience a season below the late 20th century maximum, which was much earlier than I expected. And I think this raises the question of what is a big change? And actually, this is what I was reading the email in the airport when I got off the plane last night, where collaborators were setting up some incubation experiments that I'll mention at the end, and they were saying that the CMIP-5, the climate model ensemble, doesn't simulate temperature changes that are big enough, and because it's only a couple of degrees in the tropics, and what is big enough compared to 0 Kelvin? A couple degrees is not very big, but compared to the envelope of variability that natural and human systems have experienced over recent decades, moving entirely out of that envelope is big, regardless of how many degrees that is. So to me, this is striking. I wouldn't say it's alarming, but it's certainly striking. And we can ask how quickly might this emerge in different regions, and what's the distribution of that timing? And what I'd like to focus on now, I think, is the bottom panel here, and this is the historical period. And what we've done is we've asked. So we're looking in the future. From what I've showed you, we're looking at these future climate simulations, and we've compared those future simulations with the late 20th century. And if we wanted to ask, has this emergence already been observed? Is it already happening? Can we test a hypothesis about the greenhouse gas increases that have already occurred? And if you're looking at this absolute threshold of the hottest summer of the late 20th century, then it's a tough question to ask about the late 20th century, because we don't really have a distribution of exceedances of the maximum. So what we've done is we've just moved the window backwards. We've said if the mid-20th century was the baseline, and then we look at the late 20th century, has this emergence occurred? So what you're seeing is in each of these regions is the time series of the percent of the area in the region that exceeds the mid-20th century maximum. And the purple lines here are the observations, with the raw observations being in the lighter purple and a 10-year running mean being in the darker purple. And then each gray dot is an individual climate model realization, and the black and red lines show the various means of both the mean. The black is the mean across the realizations, and then the red is the 10-year running mean of that ensemble mean. And what you see is that in the tropics, there's been a very clear and substantial emergence of unprecedented heat So the late 20th century has become considerably more removed from the mid 20th century, and that in some of the mid-latitude regions that's occurred, such as in the Mediterranean, but in other mid-latitude regions it is not as clear. And North America is another looks a bit like China. I'm not showing it on this figure, and we can ask about statistical significance and other measures of that. We can talk about that. So what this is indicating is that not only is it likely from a statistical point of view in terms of the climate model ensemble that this emergence will occur over the next few decades in large areas of the globe with increasing global warming, but also that it has already emerged relative to the earlier part of the 20th century for many regions, particularly in the tropics. And we'll skip that. So we might ask how much global warming, and that dark purple in the map was prior to the year 2040 for that 50% likelihood. And if we look in the scenario that's forcing these climate model simulations, what we see is that if we look out over the next 3 decades before 2040, that's less than 1.5 degrees of warming above the late 20th century baseline, which puts this level of global warming right around that 2 degrees Celsius above the pre-industrial that is in the Copenhagen Accord. So even within that global warming target, even if the international community were to achieve a limit on global warming of 2 degrees C above the pre-industrial baseline, then these climate model simulations are suggesting that we're still likely to see emergence of a permanent, unprecedented heat regime over large areas of the globe, particularly in the tropics where the interannual variability is much less than in the higher latitudes, which is really the cause of that. It's not the magnitude of warming in the tropics that's causing that early emergence. It's really the variability being low. All right, so that's kind of the global climate part of the talk, and I think Bill and maybe others will pick up with some other aspects of the global climate model analysis later in the sessions. The global models are pretty coarse scale, a couple degrees, getting down to 1 degree or so in the ensemble that I showed. Certainly there are higher resolution global simulations that are appearing now, but if we really want to understand the impacts of climate change, much of those impacts will be felt at local scales and will result from local scale changes. And in order to resolve those processes that create local scale climate variability, we need higher resolution models than what's available in the current generation of global climate models. There are a number of people in the room who work on various forms of various approaches to trying to get more regional and local detail. This is just a cartoon showing how we can nest progressively higher resolution models. Can be in the atmosphere, it can be in the ocean, could be in both. And most of what I'll show for the rest of the talk is using hydrostatic nesting, so 25 kilometer or so grid spacing in the atmosphere over various parts of the world. We're also, including with some of this NIH funding, trying to get down to non-hydrostatic scales where we can permit convection in the atmosphere. We can talk about those details if anyone's interested. The other frontier, which I won't talk about the details of, but I think is important for the discussion of scale, which I know will continue to come up throughout the day, is the variable resolution global modeling, which is a number of groups are pushing on this frontier, and I'm involved in one of those efforts with Los Alamos and NCAR to, rather than nesting, to have a variable resolution in the atmosphere. But the main point here is that we want to, if we want to understand, the scale that, say, a mosquito feels the climate system, we need to get down to much finer scales than the current generation of global climate models. So back to this hottest season metric that you've already heard about. getting from the global climate model scale that I've already showed you to 25 kilometers substantially improves this spatial pattern of the magnitude of that event. So the GCMs that I already showed you, this is the magnitude of the hottest season over the second half of the 20th century. The colors are almost useless without the scale, but red is hotter, blue is cooler. This is the crew is one observational data set, so just the same metric in that half-degree observational data set relative to the global models, and then our nested climate model simulations are in the middle. And as you'd expect, just from resolving the topography better, we better resolve the spatial variation in this metric. And this is temperature, but this is true for a whole suite of climate phenomena, particularly extremes, and it's not just in areas of complex topography. So if we focus in a bit on the U.S., and this is again just the counting exercise of how many seasons exceed in this case, how many days exceed some temperature threshold. In this case, this is getting down to the daily scale. So this is the 95th percentile daily maximum event. There are 365 days in most years. So just by definition, this is about the 18th hottest day of the year from year to year. And you can see that by this decade of the 2030s, around that 2 degrees warming target in the Copenhagen Agreement, areas of the U.S. are seeing either a doubling or even a tripling of the occurrence of that 18th hottest day of the year. So as one blogger put it, I think it was in response to a figure that was further out in the century, and Arizona was like 90 days a year on the map, and I had made a statement in the press like something like, well, this is like Phoenix getting 90 days of the hottest 2 weeks of the year, and one blogger responded saying, well, in my opinion, Phoenix already gets 3 months of the hottest 2 weeks of the year. But that's basically what it is, right? I mean, so even, this is 60 days, right? This is more than a doubling of that threshold, just with 1 degree of global warming. And what we're interested in, as I mentioned, are the physical climate processes that shape these changes in impacts relevant climate phenomena. And what we're seeing here is the anomalies in the atmospheric circulation, the precipitation, the soil moisture, and the evapotranspiration. And this is expressed as the decade of the 2030s in our high-resolution climate model ensemble minus the late 20th century. So brown is drier, less precipitation, less soil moisture, less evapotranspiration. And these are changes in the summer mean fields, but they're very reminiscent of what we see during heat wave events. And actually, if you look at, say, the summer of 2012 that happened in the U.S., these anomalies are very similar to what occurs. And there have been a lot of papers studying mid-latitude heat waves, and this anticyclonic circulation anomaly, drier soils, less evapotranspiration, less precipitation are very consistent physically with what we see during heat waves. And what the climate model is simulating is a shift of the summer mean towards this heat wave-like conditions. So in this case, global warming, the increase in greenhouse gas concentrations that's causing global warming is really giving a triple whammy to the surface climate. So there's the increasing long wave radiation from more CO2 and other greenhouse gas molecules in the atmosphere. But there are two other kind of boosts to the surface energy balance. One is that the decrease in evapotranspiration from the drier soils and less precipitation, that decreases the latent heat flux and partitions the surface energy balance towards sensible heat flux. So that surface moisture response, where there's less energy going into evaporating water because the water is not in the soils, that's a second whammy in addition to the long wave forcing. And then there's actually a third, which is that kind of the stabilization of the atmosphere is associated with this anticyclonic circulation anomaly, tends to create more clear sky conditions, less cloud cover, and greater penetration of solar radiation to the surface. And we see that in the incident shortwave flux over the central and eastern U.S. So there are really these, in addition just to the global warming, the regional atmospheric dynamics are changing in a way that amplifies the effect of the increasing CO2. So it's really not just a shift in the, if we get 2 degrees of global warming, then we're going to get 2 degrees of regional and local warming everywhere as well. What really matters is the response of the climate dynamics. And if we look out further in the century, if we extend these CO2 forcing experiments out beyond this near-term period, look all the way in this A1B scenario, all the way out to above 600 parts per million CO2, we see that this change in the surface energy balance intensifies with increasing CO2 concentration. So the upper left is precipitation, and you can see the shift towards progressively not only warmer conditions at the surface, but also progressively drier conditions. And what you're seeing here is we have 5 ensemble members in our 25-kilometer simulation. So each decade has actually 50 years, right? Because we're running it 5 times with the same forcing. So you have 50 dots in each of these colors, and each color is a decade. So again, intensifying decreases in precipitation over the central U.S., intensifying decreases in soil moisture, intensifying decreases in evapotranspiration, intensifying increases in the incident shortwave flux. And in fact, for many of these variables, by the last decade of the 21st century, the last 50 years in our ensemble, 50-year population, see that almost all of the years are above or below that zero line, depending on the variable. Right? So almost all of the years are beyond the mean, and so this question of the new normal becomes relevant. And if we go back to Europe, we've done similar analyses in other parts of the world, and certainly in the mid-latitudes, this is a robust response with the surface amplification of the greenhouse forcing via surface drying in the mid-latitudes. You see very similar responses in Europe with the change in soil moisture and evapotranspiration that amplifies the response of extreme temperatures to global warming. So in the upper left is the 95th percentile maximum, and this time it's the magnitude. So that 18th hottest day of the year is warming by 7 to 9 degrees over parts of Europe in the late 21st century in these simulations, and it's highly correlated spatially with the surface drying. And we can actually go back to that 2003 heat wave and ask how often do those conditions that occurred in the 2003 heat wave occur in the late 21st century climate, with in this case with basically business as usual, or actually now that Davis et al. Wedge's paper is out, maybe it's less than business as usual emissions. But in this case, it's the A2 scenario for those that are familiar. But if we take the analyses of excess deaths that have been published, so this is a paper that came out in 2005, and this is mortality on the vertical axis in France, and temperature on the right, on the vertical axis in the right, with the line plots being maximum minimum temperature. And during this period of peak excess death, the maximum temperature stayed around 35 degrees C, and the minimum temperature stayed around 19 degrees C or so during that period, and that's when the peak excess deaths occurred. So we can just do the counting exercise again and ask how many days out of the year is the maximum temperature above 35 C, and how many days out of the year is above the minimum temperature above 20 degrees C. And what you see for France, for example, is these are on the order of 20 to 25, in some cases even 30 days per year that this unprecedented severe heat wave occurs in the future climate. So this is essentially a 2003 heat wave occurring every year, 2 weeks, 3 weeks, in some cases even 4 weeks a year on average. So a very different climate that if we look at the response of human health to that kind of event in the recent past, potentially could have impacts. All right, so I'm on my last few minutes here and my last few slides, so that's a good coincidence. So the title of the workshop is infectious diseases, and I am interested to learn how what I've already showed could be relevant for infectious diseases. It might not be at all. It might just be relevant for it being really hot for people. But we do have we do have some work going that's targeted more specifically at infectious diseases, and I want to give just a brief story about corn, and then a brief one or two slides on what we're doing to try to understand fundamental relationships between temperature and disease vectors. So the relationships between corn yields and temperature have been very rigorously studied, particularly in the United States, but elsewhere as well. And this is one of those studies. It's from Schlenker and Roberts, which is not present on the screen. Schlenker and Roberts in 2009. And they've taken all the corn yield data from counties in the U.S. and taken temperature and precipitation data and done performed a regression analysis. And what they find is that there's this very steep nonlinear relationship with severe heat, so that or nonlinear relationship with increasing heat accumulation, I should say. So at low to intermediate levels of heat accumulation, corn yields increase. There's a positive relationship. We know this already, right? The Corn Belt is not, in fact, in the Arctic. Right? It's in the central U.S. For a number of reasons, but part of it is the temperature. But at high levels of heat accumulation, there's a very steep decline in corn yields, and the physiological reasons for this have actually been studied for a long time with lab experiments. And I'm going to talk about the corn for a couple of slides, and then you can start imagining now, or afterwards I'll ask you to imagine just that it's not corn, that it says something. It could be something different, right? It could be some other system for which the relationship with climate is known. And there have been some studies on different types of insects and mosquitoes and other potentially relevant biota. So this is the relationship for corn, and we can take these climate model simulations that I've already shown you and basically run the regression with the climate of the past in the simulations and the climate of the future. And what we find when we do that is that there's little response to this. There's little change in the good heat over the central U.S. over the next 3 decades. Basically, the mean shifts so that the cooler part of the year becomes warmer, the warm part of the year becomes warmer, and the mean good heat remains the same. The amount of good heat remains the same. But there's a substantial increase in the negative heat accumulation over the next 3 decades, and that causes a substantial increase in both the mean of negative heat accumulation, meaning detrimental heat accumulation to be more precise, and the variability of detrimental heat accumulation. So you can see that Illinois, for example, starts to look something like Oklahoma does at present in terms of the negative heat. And so we can ask, using these climate model simulations, we can ask a couple of questions that are highly relevant for corn, and I think could be relevant for this question of changes in range of say, disease vectors, for example. So one is we can ask what level of adaptation is required to offset the climate change. Right, so we can just look at the terms in that regression, both that critical temperature at which the negative, that steep decline in yields occurs. So we can ask, what if we move that? What if there's some adaptation that increases heat tolerance by causing the negative yields to occur at 30 degrees instead of 29, 31, 32, 33, 34, right? We can move that critical threshold. We can also ask, how steep is that decline, right? If there's some adaptation that causes the negative effective temperature to be less severe, lessens the slope of that decline, then how much decline in that slope is required. So this is the current beta. The current slope is 1, and then just fractions of that beta. And we can ask for the current, how much adaptation does it take to get back to that current value? The other question that we can ask is the spatial adaptation. So where does the current climate occur in the future? And I was already mentioning that there's very little change in the mean good heat accumulation. So that area actually falls right over the Corn Belt in the future. But what you'll find is that if we look at the negative heat, the bad heat, at least the heat that caused negative yields, and both the mean and the variability, that the future climate actually doesn't have an analog to the current climate. Right? So that space, those different variables, separate in space. So if you go to find the area of mean above the negative heat threshold, you'll find a different area than if you look at the variability of temperature above the negative threshold. Right? So we could imagine doing this kind of analysis with some other temperature relationships that maybe is more appropriate for a mosquito or a virus or something else of relevance for disease. All right. So lastly, we're actually trying to do that now in one of the NIH-funded projects. But the problem is that we lack the fundamental, at least the group of us that are funded. Maybe others don't lack it, but we lack the fundamental understanding of the relationships between temperature and the vector biology, the vector ecology, and the virus response to temperature as well. So we're setting up a number of lab experiments to try to study these. And the hook here is that we're using climate model output to generate the temperature regime that's going into the incubation. So rather than just adding 2 degrees or adding 3 degrees or adding 4 degrees, we're analyzing the climate model output to say what is the distribution of daily temperatures over these climate model simulations, and can we use those to have a physically consistent climate change that we're exposing in this case, the mosquitoes to. And one of the challenges there is we're trying to prescribe 70, 80, 90, 100 years of climate change within an incubation experiment. So there's some real challenges of how you get there from here other than waiting for 70 years. So I'm eager to talk to people about that. So just a couple of figures to close from a poster that Dan Horton had at AGU just in December. So basically we're looking across the climate model ensemble in each of these decadal periods, and we're prescribing we're basically going to run a year-long incubation experiment, a year of the real calendar, and we're going to try to prescribe this distribution of climate change that occurs over the next 70 years. Right? And so we're basically chopping up the real calendar into decades. So you get a couple weeks. If you're going to do 60 or 70 years in a year, you get a couple weeks per decade. So we're going to look at, we're taking the distribution of temperature change across that in each of those decades, and then we can take the PDF and draw from the PDF of daily temperatures to generate a 1 year long, in terms of the real calendar, time series that gets us both from the present to 2060 or 2070, but also gives us the physically consistent response of daily temperatures that's simulated in the climate models. All right, so I'll close with the conclusion slide up and just say that, again, that I think this is a really exciting fertile area of research in terms of understanding not only the impacts of climate change, but also the physical dynamics of climate change. I think we can, just like with corn and with other impacts, I think we can use disease as a probe for understanding the physical response of the climate system to global warming. And in many cases, maybe we already know enough about the fundamental relationships, but I think in a lot of cases, as was mentioned in the introduction, we need work at the very in the lab and in the field without before we go into the future with projections of impact. So thank you very much for your patience, and I'm happy to take questions as there's time.